You know how
Okay. All right. Let's get started. Okay. Please, I can't whistle. All right. Thank you. All right. Let's continue. Finish up fat lecture. So now you all have done the Mojonnier or Mojo method. And this is a discontinuous solvent extraction. So SE is for solvent extraction. So as you all have seen, is the sample is directly weighed into the flask or in a weighing bowl and you transfer it into the flask. Cheese groups did not see that because we had to digest or solubilize with ammonium hydroxide the night before. And usually with cheese, we do that specifically because the cheese curd, the protein forms a curd and the fat is entrapped within that curd. So basically we use ammonium hydroxide to kind of solubilize the protein, break up the curd so that the fat can easily be released, so that the solvent can extract better the fat. Ethanol is added to prevent clumping because if you don't have ethanol, the protein might clump together when you add the ethyl ether and petroleum ether. And if the protein clumps, it might entrap some of the fat, and that can cause underestimation of your fat content. So one of the questions of your lab report is going to ask you about reasons for underestimation. That could be one of the reasons if you mess up adding the ethanol or you added it late, then you might have clumps and the fat will be entrapped and will be extracted as well with the organic solvents. So both ethyl ether and petroleum ether are used. It's a good combination. Petroleum ether is a better solvent for non-polar lipids, so basically your triglycerides, and ethyl ether can solubilize non-polar, but also is a good solvent for polar lipids. So a combination of both should give you a good extraction of the different lipids of different polarities. And we afford to do that in Mojo because we use small volumes. I believe it's 25 milliliter of each. Whereas in Soxhlet, if you remember, it was a 350 milliliter per one sample. So it's a lot of solvent, and ethyl ether is more expensive than petroleum. Moisture removal from sample in this case is yes.
Can you go over ethyl ether for
ethyl ether is a good solvent overall for lipid for combination of polar and non-polar. Whereas petroleum ether is not a good solvent for polar lipids. For example, phospholipids, it won't be a good solvent for it. Petroleum ether is the better solvent for triglycerides, for example. So using a combination can basically get you most of your lipids, the polar lipid and the non-polar lipid fractions. Okay, so in Mojo, you don't have to dry the samples. So the cheese samples, for example, were not pre-dried. There is a shaking step in Mojo. So it's basically, even if you have moisture, but that shaking allows the solvent to basically solubilize the fat regardless of the amount of moisture there is. Whereas in Soxhlet, we don't have that motion, we don't have that shaking. And if there is moisture in the sample and the solvent is dripping on your sample and there's a lot of moisture, it's not going to be able to penetrate and extract the fat properly. For samples that are high in carbohydrates, we do a digestion step, such as your samples Cheerios or baby cereal or almonds. You have not necessarily high in carbohydrate, you have protein in there and fiber. So the HCl helps digesting other components so that the fat that is interacting with other macromolecules is released and better extracted by the solvent. So for samples that are high in carbohydrates, when you get your data, you're going to see that data is more accurate when using Mojo than when using Soxhlet. Because Soxhlet is not really intended for low-fat samples and samples high in carbohydrate. It doesn't have that digestion step prior, so you don't get that release of the fat very well. It's really well suited for high-fat samples, especially meat and nuts. So Soxhlet is really good for that. You're probably going to see good, potentially acceptable results for cheese, but Mojo will be the better one because of using the ammonium hydroxide that breaks down the gel matrix and allowing the fat to be released. Questions? Okay. So other forms for extracting fat, and usually this is used mostly for defatting as a defatting step prior to another analysis or another process, but it can be used for determining fat content, but it's not common used for determining fat content. So elevated pressure and temperature. Under this category, we have supercritical fluid extraction, SFE, and we have accelerated solvent extraction. We'll talk about it in the next slide. So in this supercritical fluid extraction is when you have a gas like CO2 and you increase the pressure and you increase the temperature above a critical point, then CO2 becomes liquid, fluid. So it can be used then to extract fat. And it's a very, the fluid has a hydrophobic characteristic, so it's good for hydrophobic non-polar components. And sometimes if you want to enhance the extraction of polar lipids, you can add methanol because it's a little bit relatively polar solvent. But if you're extracting fat and you know that most of your fat components or lipid components are non-polar, then just using CO2 under the supercritical conditions is sufficient. So basically you have a tank for CO2 and then it gets pumped into a cell where you have your sample, it gets heated, and then what happens is the solvent is soaking the sample, extracting the fat, and then the solvent is then moved into a collecting vial, and as soon as it reaches the collecting vial, the pressure drops. And by the pressure dropping, the CO2 evaporates, obviously turns into gas state, and then you collect the liquid or fluid fat or lipid in that vial. So that's how it works. I have a note here that it can be coupled with GC if we are extracting components that later on we want to analyze using gas chromatography. So supercritical fluid extraction can be coupled with further analytical tool such as GC. The elevated pressure temperature in terms of another method is accelerated solvent extraction. Here we don't use CO2, we use regular organic solvent. But in this case, you have your regular solvent, it gets pumped, and then what happens is it goes into a chamber where the pressure is increased. So the boiling point of that solvent is now higher. By increasing the boiling point of the solvent, you enhance the efficiency of extraction at higher temperatures. So instead of having the solvent evaporate very quickly, it stays with the sample, and the higher temperature helps with better extraction due to kinetic energy and help with movement of the fat or solubilization of the fat. So you can use it as a soaking mechanism where it is static. So this valve is closed, so you soak and then you open it to allow collection of the solvent with the fat. Or it can be dynamic mode. So this is open and we're always adding solvent, kind of like continuous extraction, solvent extraction. So you always add solvent and it's going to go into your sample. But this is If you have it in dynamic mode, that's a lot of use of solvent. If you have it in static, you can actually have it in static and dynamic at the same time. You can have like semi-continuous extraction. So you can have it a little bit closed with the soaking effect. You open it, allow the solvent to go through, and then maybe another cycle of solvent, close, soak, and then open it again. So you can play around with the setup, either have completely continuous extraction or a batch extraction or a semi-continuous extraction. If you do that and you're using solvent, if you want to determine the amount of fat, you have to evaporate the solvent like we did for the module. So you remove the solvent in order to get away with the fat. Here, and you don't have CO2 that just automatically become gas at, when the pressure is reduced. You actually have a solvent, so you need to get rid of the solvent to measure the fat content. Okay, another method that is non-solvent based, and it's mostly for dairy, is Babcock method for extraction of milk fat or dairy fat. So we can use it for milk, cream, or cheese. You notice that for cheese, you cannot obviously weigh the cheese or have a certain volume of the cheese that goes down. You just have to put the sample here. So that's why the shape looks different if it's milk versus cream versus cheese. So what happens in this case, you use sulfuric acid, concentrated sulfuric acid. So a specific volume of your sample, I believe it's 17.6 milliliter. It means nothing to you, but just say specific volume of sample is put here, and then you add the exact same amount of H2SO4, the same volume of the concentrated acid. So once you have a concentrated acid with your food, it's an exothermic reaction. So you start generating heat. So the heat generated with the acid, you will digest the protein and the fat will be released. So what then will happen is the fat will be released to the top, and then you're going to measure the fat content volumetrically by measuring the volume. So you're going to get the volume of the fat. So there is centrifugation step to help the fat separate properly from any aqueous, and then you measure it by measuring the volume. And this is the graduated neck where it starts from 0 to 20, and then you can measure the volume. It is designed in such a way that you have to have a specific volume of sample, not more, not less, so that you get a reading within this size of a neck for the flask. We don't need to dry the sample, so you just measure as is. Gerber method is very, very similar. It does just have a different shape of the flask. And it uses, in addition to sulfuric acid, it uses amyl alcohol. So isoamyl alcohol specifically, if you have sugar in your sample, it will prevent charring of the sugar. So when you have sugar and you have H2SO4, you will have like blackening. So that's what the charring means. Blackened, it might kind of cause make it hard to read the volume. So adding the amyl alcohol prevents this charring. So it helps with better reading, basically. But other than that, it's just very similar to that. Both methods are volumetric, whether it's Babcock or Gerber, and we can use the volume of fat to calculate percentage of fat on what basis. So take out your sheet from last time for the +2 and start solving this question. So here we have 3.55% on a volume basis. That means 3.55 milliliter of fat in 100 milliliter of milk. We want to convert the volume into percent weight. You have densities. So go ahead, think about it and convert. Do you have an answer, anybody? You know what you need to do, right? You need to convert the volume to mass using density. Density equal mass over volume. So 3.55 milliliter of fat, that's the density. So convert 3.5 milliliter of fat into mass using the density. And then the 100 milliliter of milk, this is 3.55 milliliter and 100 milliliter of milk. You convert the 100 milliliter of milk to mass, and this is the density. So density equal mass over volume. So you get the mass of the milk of 100 milliliter milk, and then the mass of the 3.5 milliliter of fat. Does it make sense? We have 3.55 milliliter of fat in 100 milliliter of milk. You want to get the percentage in weight by weight basis. So you have the milliliter of fat that you convert using the density of fat, and you have 100 milliliter of milk you convert to mass using the density of milk. Then you get grams of fat in the total grams of milk, and you convert to percentage. Anybody with an answer? Yes, Grace.
3.1% fat.
Yes. There it is. So milliliters times the density, because density equals mass over volume. If I have the volume, I need the mass, so it's volume times density to get the mass. So now I have this amount of fat. And in 100 milliliter, again, I multiply by my density for milk, I get 103.2 grams of milk. So I have this much fat in this much milk, and then I multiply by 100 to get the percentage in on weight basis. Yeah? Oh, don't take me there. Don't take me there. More than two significant figures. Let's see. Yeah, maybe. What do we have? How many significant figures do we have? So, well, this shouldn't have four significant figures anyway, right? Because of what I'm multiplying. Let's not talk about it. I really don't like that subject. Okay. So you can do fat analysis using instruments. We haven't covered NIR yet. We will cover it on Monday, but we can use NIR instruments or mid-IR instrument to measure amount of fat based on the IR absorption or energy absorption by the fat. We'll talk more about that on Monday, but any infrared spectroscopy has to be calibrated against the standard method. So if you remember from the beginning of the semester, we talked about primary methods, secondary methods. So primary methods are your standard official methods of analysis. And then secondary methods are quality control, fast methods that are not necessarily official methods of analysis. So they have to be calibrated based on an official method. The way you calibrate an IR unit is you would have, let's say, if you're measuring fat content in milk, you would prepare milk samples that have different fat contents. You actually prepare your standards to be the milk sample actually at different fat concentration. And then you measure the fat content using Mojo, for example. And then you enter the absorption you get by IR of all of the different milk samples, and you plot it against the actual concentration that you have gotten from the official method of analysis, generate your calibration or prediction equation, and then you can potentially convert the absorption by IR to a concentration. So it has to be calibrated. You don't always have to run standards. You just have to check the instrument every now and then. It didn't deviate from the calibration. But once it's calibrated, you can run a lot of samples to determine fat content. Not just fat content, as we're going to learn later. We can determine a lot of different composition using IR. Bosley method is not really very commonly used, but it's based on the specific gravity of the extract of the solvent that has the fat extracted. And usually you determine the specific gravity and then use a conversion chart to convert the specific gravity to fat content. Lastly, NMR. While the principle is complex, the method is easy. It's highly automated and it gives you rapid analysis of fat content. Okay, any questions about fat? We have 20 minutes. I'm going to start proteins. All right. So let's answer this. What do you remember from your food test? The following absorb light. Yes, yeah. A and C. Yes. So tryptophan is an aromatic amino acid. There are 3 aromatic amino acids, and these are tyrosine, tryptophan, and phenylalanine. So these 3 absorb light at 280 nanometers. So these are the only 3 amino acids in protein that absorb light at 280 nanometers. But all proteins, all food proteins, contain a certain proportion of all of these 3 amino acids. So therefore, a solution of protein, if it's pure, you can use as absorption to measure protein content at 280 nanometers. So, what are you doing?
No, just like, because they don't eat it, so would that just be like really dark, or would that just be?
No, because they all proteins contain these aromatic amino acids, proteins in general, absorb at 280. So you can have a protein standard and you can run your protein standard at different concentration. and run the absorption to 80 on a standard curve, then get your sample and run it, turning the absorption, and use the equation to line to get the concentration of the protein. So, but the caveat here with using a UV method that protein, your sample has to be very pure in a sense, clear solution first, not a lot of components that may absorb it to 80. Then there are other compounds, phenolic compounds that might absorb it to 80. So your sample has to be usually a pure extract that you are measuring the protein content after you extract or doing analysis with chromatographic analysis. You can use, if you're looking at protein, you can use a PDA, for example, or a variable UV detector to detect your protein. If you're looking at peptides, that means if you have a protein that is hydrolyzed, broken down into segments, not every segment will have potentially aromatic amino acids. So when you're measuring peptides, we can use different wavelengths. And this brings me to ask you about peptide bond. What do you know about a peptide bond? Shri? A. So A is correct. It's a covalent bond. Yes. B and C are incorrect. What is it? It's a covalent bond, and it's a bond between what and what? Go ahead. I'm going to go with Elizabeth. Okay. Yeah, it's the carboxyl group of one amino acid and the amino group of another amino acid that gives me a peptide bond. So why do I care to know about this in food analysis? Because peptide bond absorb light. So we can measure a protein absorption at 214 to 220 nanometer, where the peptide bond absorb UV light. So there are different methods based on absorption of light that we can utilize to determine protein content or presence of protein or peptides in a sample.
And why is it not being on the previous slides?
It's not a bond between
Oh, because it's never mind.
carboxyl group. Yeah. It's not a bond between two amino groups. It's a bond between the amino group of one and a carboxyl group of another. Amino group of one, carboxyl group of another. That's your peptide bond. Okay. Any other questions? Why do we care? Why do we analyze proteins? That's very good. We need to know, we need it for the nutrition label. What else? Dora? Related to health? Yes, for health purposes, we need to know how much protein we're consuming, but when it comes to health, we're going to learn about this in the protein characterization. We need to know the daily value. So we need to take into account the digestibility of the protein.
Potential reactions.
What's that?
Potential reactions that could occur.
Not easy. Protein change. So again, nutrition label. All right. Page.
Standards of identity.
Yes. Yes. Standard of identity. Yes, sir. Yes, they have function. Thank you, protein lab person. Thank you. Proteins function. We need to determine functionality based on the amount of protein in the sample. So we determine that. What else protein group people? Ellery. It's okay, you're not protein group. You are welcome to come.
Thank you.
I thought when you have to like pull up all the macros in the food samples and find the total carbohydrates.
Oh, yeah, so it is definitely needed kind of like approximate analysis, which is hence the approximate analysis, but there's flavor. Okay, so your answer is similar to you. Okay, we care about Maillard, we care about flavor, but it's not necessarily why we get content. Anybody, Michael, hesitation?
I was gonna say something about, because Gary was talking about how, flavor compounds bind to protein.
Yes,
Right, but
okay,
you're
the
right,
more
what you just
protein
said
you
is-
have, the more the flavor is.
Yeah, yeah, you're right.
Okay. Product formulation. Yes, yes. Okay, I didn't have it as one of my, but yeah, we need to know how much we're adding protein, obviously, to our formulation. But here it is. So, as part of the specification standard of identity as a quality control, we need to determine protein content, nutrition label, functional properties. One thing we didn't mention is reduction of protein ingredients. So when you're producing a protein ingredient, you want to determine the efficiency of your extraction. You want to determine how much protein you end up in your final ingredient. So you need to determine protein content. We talked about functional properties, biological activity determination, especially if it's an enzyme. You need to determine the activity of enzyme per gram of protein. So the enzyme is a protein and you need to determine its activity. So you need to know the content that you have. Or if it's another biological activity, let's say if it's not an enzyme, it's a bioactive peptide, and you're measuring antioxidant activity, or you're measuring hypertension activity or anti-hypertensive activity of the peptide, you need to determine how much protein you have so that you can determine the activity for the amount of protein that you have. So many methods out there for protein determination. You're going to learn in class, in lab next week, two of the official methods of analysis that I use commonly for nutrition labeling. Kjeldahl, which is a chemical-based method, and Dumas, which is an instrument-based method. Both are based on measuring nitrogen content. So we're going to talk about these in detail. And then IR, that's a fast method for determining protein content in different types of samples. And then you have the research methods, where you have a purified sample of protein and then you can determine it using absorption. All of these methods are based on interaction of the protein and the reagent to give you a color and you measure it, except the UV, which is based on the natural ability of the protein to absorb light due to these aromatic amines. So different methods, we're going to talk about them, not all of them, but most of them. My favorite method of all time. Don't I have a lot of favorite methods? So Pam is pathetic. She likes them. Okay, so Kjeldahl. It's one of the oldest methods and most accurate methods for protein determination if you do it right, if you know what you do. So basically it determines the amount of nitrogen, and you convert the amount of nitrogen to protein based on a conversion factor. So we'll talk about that. So the method involves multiple steps. First, digestion with a strong acid. Second, neutralization with a strong base coupled with distillation. Neutralization and distillation happens together in one step. We'll talk about that. And the final step is titration. In all of these steps, we're following the nitrogen. We follow the nitrogen after digestion, neutralization, distillation, and finally titration to calculate the nitrogen content. Once we get the nitrogen content in percentage, we multiply it by a conversion factor. Every protein source has different percentage of nitrogen. Why? Put chemistry hat on. Why every protein might have different percentage of nitrogen? Wait a second. Wait a second. You both are good at answering, and then other people. To be not shy, and it's okay not to know. You do it. Tell me. Okay, no pressure. No pressure. All right, so come on, what proteins are made up of what? Maya, proteins, what are they made up of? What's the building block? Amino acids. Do all amino acids have the same nitrogen content? Maya? Do all amino acids have the same nitrogen content? No is the correct answer. No, you have basic amino acids that have extra amino groups in them. So the protein is different in composition of amino acids. So basically you have a difference in percentage of nitrogen across different sources of proteins. So based on the percentage of nitrogen, you have a conversion factor. But this one, 6.25, is the common one used because on average, you have 16% nitrogen in a protein. That is the average. But for example, cheese is low in basic amino acids. So the conversion factor is 6.38 because it has a lower percent nitrogen. Wheat, for example, so those of you that will materials, you'll notice that we're going to use a 5.7 conversion factor because wheat has higher amount of basic amino acids. So it's not 16%, it's a little bit higher. So when the percentage is higher, the conversion factor obviously is lower. But when we don't know, or when we have a blend of protein, the mixture of proteins in a food product, you have a lot of different sources of protein in cake. You have egg protein, you have wheat protein, you have other sources that goes into the cake making. So when I want to determine the protein content in a cake mix, I use 6.25 conversion. Now, why is this a crude way of measuring protein content? Crude, not actual amount of protein in the sample. Grace?
There could be other compounds in the food.
Absolutely. So nitrogen doesn't only come from protein. Some vitamins have nitrogen in them. Nucleic acids have nitrogen in them. It's ammonia. So ammonium salt, if you have any salt with ammonium salt in your sample. So basically, it's a crude method because it's based on nitrogen content or amine groups that are not coming from the protein itself. So that is why it's a crude method of analysis for proteins. But still very close. All right, so these are the four steps. The fourth step is calculation, but it's 3 chemical reactions happening. And please remember that number 2 is actually neutralization / distillation. We are neutralizing and distilling in this step. All right, so the first step is digestion. So you have your food, we add to it concentrated sulfuric acid. And we add a catalyst. The catalyst is added to do 2 things. First, speeds up the reaction. That's the definition of catalyst, speed up the digestion. Otherwise, it would take hours and hours to digest. And what it does too, it increases the boiling point of sulfuric acid. So when we're heating it really high temperature, sulfuric acid might evaporate rather than digest the food. So the presence of the catalyst increases the boiling point of sulfuric acid, so it stays with your food to digest the food. So what happens when you add sulfuric acid, different organic matter is going to be combusted. So you get CO2, H2O, SO2. Your ammonia or amine groups, are going to react with the sulfate from the sulfuric acid. So you're going to form ammonium sulfate. I make that in red because we're following the nitrogen in the reaction. It's a chemical reaction, so I'm going to explain it based on chemical reaction. So ammonium sulfate remains after digestion. Everything else organic becomes fuel and leaves the sample. Now you have soluble ammonium sulfate in the sample, you neutralize. We neutralize with NaOH. So what will happen is you get ammonia, and ammonia is vapor, is gas. So we don't want ammonia to just go out, we need to contain it. Because we need to contain it, we distill it. So we make sure that the ammonia evaporates along with water. We're going to have water generated. So the water and ammonia both are going to evaporate, and then there's a condenser, and they will be condensed into a solution containing boric acid. So instead of the ammonia evaporating and leaving the system, we need to contain it. So there is a distillation step that brings the ammonia down to react with boric acid. In this case, we have an indicator, methyl red indicator. With boric acid, the methyl red is red, color red. When you have ammonia, you form ammonium borate. Now this is basic, then it will convert yellow. So now you have a yellow solution because now you have ammonium borate. All right, so now we titrate. The last step is titration. We titrate with HCl. So now I'm titrating. We have 1 mole here to 1 mole here to 1 mole here. 1 mole of ammonia, 1 mole of borate, and 1 mole of HCl in this reaction. Okay, 1 to 1 to 1. So the number of moles of HCl needed to neutralize ammonium borate would be equal to the number of moles of nitrogen. So 1 nitrogen, 1 mole of ammonia, 1 mole of borate, 1 mole of HCl in bacterial chemistry. Okay, so when I titrate, I have yellow. I titrate with acid. The last drop is going to turn everything pink. At neutralization, you end the titration, everything turns pink. At that point of neutralization, numbers of moles of HCl equal number of moles of borate equals number of moles of ammonium equal number of moles of N. We use that to determine percent nitrogen. And we are going to derive the equation next time together. So I have a couple of minutes yet, don't go. I'm not going to derive the equation now, but I'm going to show you the apparatus. This is what you're going to use in the lab. This is a digestion block. This is going to be done for you actually because the digestion takes several hours. So each tube here will have your sample, will have H2SO4, and will have the catalyst. And this is the heating block. And there is an exhaust system. The fumes are going to be pulled up with the exhaust system and neutralized. They don't go into the atmosphere. So after digestion, you end up with a clear solution. It's blue because of, remember what the catalyst was? It's copper sulfate. So you have a blue digest, clear. All of organic matter oxidized, bring up into fuel. You have the ammonium sulfate in here. This is the neutralization distillation unit. So in the back of it, there is a reservoir of NaOH. So we introduce NaOH here. The reaction generates heat. It's an exothermic reaction. Ammonia and H2O will evaporate, condense, into the receiving flask of boric acid. And that flask gets titrated with this. So this is kind of illustration of what happens. I'm sure you're ready to go, but I'm not ready to stop. That's okay. I'll continue on Friday. Do I want these? Not yet. Keep them with you. We have more calculations next time. What's the set?